Yeah, today we're just going to wrap up the Section 5 and Chapter 6 with a couple of topics, hybridization and also intermolecular forces. Hybridization kind of tells us how it works to make molecules symmetric. If I have several different orbitals, for instance, with carbon, carbon has electrons in the 2s orbital and the 2p orbital. So really, you would think that it would have, we know the 2s is going to have one orbital with 2 electrons, and the 2p is going to have 3 orbitals with 2 electrons each. So s and p are different orbitals. How would that work? Well, it turns out when bonding, and I know there's a lot of words here, but I'll try to keep it short. When bonding, what happens is the 2s and the 2p orbitals hybridize to form 4 identical orbitals. And we're going to call those sp3 because it's going to be 1s orbital and 3p orbitals combined. And then you're going to have, it has an energy somewhere between 2s and 2p. So those 4 hybrid orbitals are going to be in the middle of 2s and 2p. And this is how we can explain the geometry, because otherwise, if you had it wouldn't make a whole lot of sense. You have different orbitals. How would those geometries work with the valence electrons? So we just want to realize that there are hybrid orbitals that are formed to make those bonds work. We have linear geometries. We get an s orbital and a p orbital combining to make an sp. And by the way, that's just saying it's really s1, p1, but we're just leaving out the 1 like we do in algebra. So we would have an sp orbital, 2 sp orbitals basically. With the trigonal planar, we would have 3 sp2 orbitals. And with the tetrahedral, we would have, like we just said with CH4, we're going to have 4 sp3 orbitals. So it sounds a little complicated, but I hope I was able to simplify that a little bit. Because now we're going to talk about intermolecular forces, sometimes abbreviated as IMFs. So we've been talking about bonds within the atom, between the atoms within the molecule. But molecules actually have a somewhat strong bond with each other sometimes. The bonds between molecules are never as strong as the covalent bonds within molecules, and covalent bonds are never as strong as ionic bonds, but they do have an effect on things like the boiling point and some other properties, for instance with water. We're going to talk about 3 main ones, main intermolecular forces, 3 types. And just remember, ionic compounds are still going to be higher in boiling point than in melting point than covalent substances. But right now we're just talking about the forces between covalent substances. So first, before we talk about the first type, we need to define something called a dipole. All a dipole is something that's charged. It has a positive charge on one end and a negative charge on the other end. And an example of that would be a hydrogen chloride molecule. We know that chlorine has a much higher electronegativity, a much higher propensity for electrons than hydrogen does. So it's going to be pulling those electrons closer to it. We actually have a symbol to represent that, because you're actually going to see a partial negative charge on one side. That's the lowercase Greek letter delta. You can see a positive, partial positive on the other side. We draw the arrow to represent a dipole. It shows that the electrons kind of get pulled toward the chlorine.
So how does partial positive and partial negative work?
So it's essentially like that's a good question. The chlorine is pulling the electron towards it, but it hasn't quite fully. We're not at the point where it's a complete separate ion. Like if I had H plus and Cl separated, we would easily be able to see that, this definitely has a negative charge. This definitely has a positive charge. But within a molecule, it's pulling the electron towards it, but it's not completely on that side. So we're just saying it's not quite a full negative charge, but it's kind of partial. Partial is the best way to describe it. Like it doesn't have that full. It hasn't completely taken over the electron at that point. I don't know if that answers your question, but sort of like if you're playing tug of war and you haven't won yet, but you're winning. It's kind of like that idea where you haven't fully won, but you're in the process of winning because you're pulling the other side to your side. That's a good question, though. Had me a little stumped there. So the first type is going to be between these dipoles, the dipole-dipole forces. So if I had two HCl molecules, and we do have that partial negative on the chlorine side, we're going to see a slight attraction for the positive partial charge on the hydrogen. And we can use a dotted line to represent that. And again, we can keep drawing that partial positive on the hydrogen, maybe have another molecule down here. And the partial negative side gets attracted to the H. And that's why you have these molecules are sort of sticking together in a way. Note that dipole-dipole forces only work at a short range. And the stronger you have electronegativity difference between two molecules, you see the higher the boiling point is going to become, the stronger those dipole-dipole interactions are. Versus bromine Br2, that molecule does not have a strong electronegativity difference. You're not going to see strong dipole-dipole forces, and you can see, as a result, has a much lower boiling point. We see that in some of these molecules here. The higher boiling points tend to go with the polar molecules, especially water has a boiling point of 100 degrees. And just be aware that polar molecules can actually induce a dipole temporarily. For instance, if we look at an oxygen molecule, we know an oxygen molecule, completely nonpolar, doesn't have a charge. But if I brought a water to it, remember, water has that bent shape, so you are going to see a partial positive charge in these hydrogens. What that could do is these partial positive charges could actually bring the electrons just ever so slightly more towards one side of the oxygen molecule. And that's actually how water helps oxygen dissolve. That's why oxygen can dissolve in water, because you're not creating a dipole, but you're essentially inducing one by bringing the hydrogens close to it. So there is a very, very strong form of a dipole-dipole interaction, and that's in compounds containing hydrogen, because remember, hydrogen essentially has no interest in electrons. Fluorine, oxygen, and nitrogen have very high interest in electrons. So you're going to see those partial positive charges on the hydrogen side of these molecules and partial negative charges on the other side of these molecules because of those electronegativity differences. So this strong dipole-dipole force we call a hydrogen bond. And it's actually the strongest of the three intermolecular forces we're going to talk about. It's really when hydrogen atoms bond with the negative side of other molecules when they're in a molecule. That's what we call a hydrogen bond. And we see that really represented with water. It's an important aspect of water. It's why water sort of clings to itself. You'll notice water beads up together. It doesn't just spread all over the place. That's how capillary action works when plants are using their tubes to get water, because water will adhere to the sides of things because of those hydrogen bonds. It's also what gives water its high boiling point as well. But those dotted lines are representing the hydrogen bonds. And although they're strong, they're still not stronger than the bonds between the hydrogen and the oxygen itself. That's why these are intermolecular forces. But so remember, hydrogen bonds are your strongest of the three, but then your weakest of the three, this last one we're going to talk about, are the London dispersion forces. It's actually not named after the city of London. It's named after this guy, Fritz London, who proposed it in 1930. But basically, this is the idea that molecules are chaotic. The electrons are constantly moving around. So even noble gases experience this weak intermolecular force between each other. So basically, just at a particular frame in time, a point in time, you might have an electron far away on one side of a molecule, that on another molecule it's close, and so you temporarily induce a slight, ever so slight attraction. So just this chaotic motion of molecules and electrons is just constantly causing slight forces between any molecule. So these things always exist between molecules. They have to be accounted for because molecules do attract each other, even if they're not polar, even if they're not exhibiting those hydrogen bonds. You're still always going to have these types of forces called London dispersion forces. So that's all I have for you with the intermolecular stuff. You guys